Hello students, today we learn the practicals from dynamics of machinery. The aim of this practical is to study the longitudinal vibrations of spring mass systems. So let's we start our practicals, that is to study the longitudinal vibrations of spring mass systems. Before we start the practicals, first of all we learn the theory. In spring mass system, as we all know that there are the one springs and one mass. The mass m is attached with the spring, and the one end of the spring is as fixed. Now you can see that here in below you can see that there are the spring with stiffness K. You can see that the spring with unloaded positions and loaded positions. So there are the mass M is attached with the spring. So after placing the mass after placing the mass at the end of the springs, you can see that due to the mass there will be the delta deflection. So there are the delta static deflections due to the mass m. So what happens if there are the static deflection delta, the downward there are the mg force, and upward due to delta deflection there are the spring force k into delta. So you can see that here there are the mg is downward and upward there are the k into delta. K delta is nothing but the spring force. Now, what we have to do, we have to find out the vibrations of spring mass system. So we have to given the small x displacement. So here you can see that here the small x displacement is given. So if we give the small x displacement, then there are the downward mg force, and upward there are the total now you can see that the total displacement of the spring is small x plus delta. Delta is the static displacement. So you can see that the total displacement is total displacement is x plus delta. So you can see that the upward spring force k is k into x plus delta. Now there are the inertia force also act in particular systems, that is m x double dot. Now, for the equilibrium methods, if we consider the equilibrium method, for the static deflections, we know that mg is equal to k delta, and when we give the small x displacement, the equations becomes mx double dot plus kx plus delta is equal to mg, because here downward force is equal to the upward force. So upward there are the k into x plus delta and mx double dot, and downward there are the mg force. So upward force is equal to downward force. So we get the equations like mx double dot plus k into x plus delta is equal to mg. If we simplify these equations, we get mx double dot plus kx is equal to 0. So now we have to compare our equations with the standard equations of simple harmonic motion. So we have to set our equations as looks like the simple harmonic motion. So we have to make further simplification, that is x double dot plus k by m x is equal to 0. Now we have to compare our equations with the simple harmonic motion equations, and that is equal to x double dot plus omega square x is equal to 0. So if we compare these equations, we get that omega square is nothing but the k upon m. So we get omega is equal to under root k upon m. So this is the natural angular velocities. So it is omega n is equal to under root k upon m. And we know that frequency is nothing but the omega n upon 2 pi. So frequency we get 1 upon 2 pi into under root k upon m. So this is the theoretical equations we use to calculate the frequency of spring mass system. Now what is the definitions of frequency? Frequency is nothing but the repetition motion per unit time. So in practicals, we have to use the definitions of frequency to find out the frequency. And according to the definitions of frequency, Fn is equal to number of oscillations divided by actual time period. So practical, we have to use Fn is equal to number of oscillations divided by actual time period. What is the procedure for our practicals? The first of all, we have to fix the spring one end. So here upper end of the spring we have to fix, and then we have to measure the length of the spring at initial level. So when there are no mass is attached with the spring, we have to measure the length of the spring, that is called as the free length. And then we have to put some weight on the platforms and note down the deflections of the spring. So how to get the deflection? Deflection is nothing but the final length of the spring minus the initial or free length. Now what we have to do, to vibrating the systems, we have to given small x displacement, and then we have to count the time, or we have to measure the time for the 10 oscillations, 20 oscillations, or whatever we want. So here we consider it 10 oscillations, and for 10 oscillations we have to measure the time by using of the stopwatch. And so this time is nothing but the actual period. But for the accuracy of our result, we have to repeat our process for the 3 times. So this is the procedure for spring mass systems, vibrations of spring mass system. Here you can see that the considerations. Here the mass m is considered, that is 1.2 kgs. The initial length of the spring is 70 centimeters, and after placing the mass, the final length of the spring will achieve as 100 centimeters. So deflections we get delta is equal to 100 minus 70 centimeters, that is 30 centimeters. You can see that in our videos. Here the initial length of the spring is 70 centimeters. You can see that in our scale. So the free length of the spring, or you can see that free length is 70 centimeters. Now we have to place the mass. Here the mass weight is considered as 1.2 kg. So if we place the 1.2 kg mass, the spring will stretch, and we have to measure the final length of the spring after placing the mass. So here you can see that the spring is in stretch positions. So we have to measure the final length of the spring after placing the mass. So So if we measure the spring length, we get 100 centimeters. So the deflections we get 100 minus 70 centimeters. So spring stiffness K is nothing but the omega W upon delta. So W is M into G. Here M is considered as 1.2. So 1.2 we have to consider uh, M, and G is 9.81 meter per second square, and delta we get 30 centimeters. So in meter, 30 into 10 raised to minus 2. So we get K is equal to 39.27 Newton per meter. Now in practicals, we have to measure the time for the 10 oscillations. So first for that we have to give the small x displacement in our spring mass systems, and the times we have to measure by using the stopwatch. Here small x displacement is given, and vibrations is starts. So we have to measure the time required for the 10 oscillations. So first readings we get, that is equal to 11.26 seconds. Now we have to repeat this process 3 times. Again we have to follow the same procedure. So second times we get reading is 11.01 seconds. So here we take the readings 3 times for the 10 oscillations, that is 11.08 second, 11.01 second, and 11.26 seconds. So the frequency Fn is equal to number of oscillations upon actual time. So there are the Fn is equal to 10 upon 11.11. Here the number of oscillation is 10, and the time actual time period we consider it as the average of these three readings. So that is equal to 11.11. So we get frequency fn is equal to 0.910 hertz. So practically we get the frequency is equal to 0.910 hertz. Now if you look at the theoretical equations of frequency, that is fn is equal to 1 upon 2 pi under root k upon m. So here k we get 39.27 and the mass m is 1.2. So if we place the value of k and m according to our conditions, we get the frequency is equal to fn is equal to 0.900 hertz. So we can see that theoreticals and practicals both value we match with each other. So in these practicals we learn how to calculate the longitudinal vibrations or longitudinal frequency of the spring mass systems. Thank you.